Hi, thank you everybody for coming. I was expecting a much smaller number of people. This talk was prepared mostly for friends and family, people we know, get to meet very rarely. So it's much larger crowd. Thank you all for coming. We greatly appreciate it. Thank you for your interest in Ozone. My name is Anu Engineer. I'm an Apache contributor, and this is Jayu. We have been, both of us has been contributing to Ozone for quite a few years now. It's been a journey, and this talk is about how Ozone scales, how it will eventually help HDFS to scale. It was a slightly clickbaity title because we are in a journey, and this is like a halfway point. So HDFS does not scale today, but it worked. A lot of you are here, so thank you very much for once more for coming by. So here is the backstory of Ozone. A lot of you have heard it. For new people, HDFS fundamentally was designed for a particular design point where it assumes that you're going to put large amounts of data, but it is going to be in files which are very large. So you have one file, but it's really large. But when people started using it, it started to be used in a way where people would put a lot of small files. And when I say a lot of small files, you go home in the evening, come back up, and somebody was just telling me, overnight you come back, there are 5 million small files. When you went home, HDFS was good. You come back early in the morning, HDFS is not doing very well. Then generally, as an HDFS person, what you do is that you find the person, shoot him who did that, so on and so on. So, but most people who work with HDFS have seen that problem. And this happens because HDFS keeps all this metadata about these small files. Somebody wrote a 1-byte file, and there was a demo that I saw recently which scans for 0-byte files. Yes, you allocate a 0-byte file, name node allocates 100 bytes in memory. So that becomes a pain point pretty quickly. Ozone was designed to address that problem. Okay. Now, as I said, I'll show you how that happens. Now, this is a well-known problem of HDFS, and we have had a lot of work gone into this in various ways. So there was a block, how do we separate block management? These are various JIRAs and proposals from the community. Ozone liberally borrows from all of these. So I just want to thank every proposal that has come before us, and which has helped us tremendously. Ozone, current state of Ozone is that Ozone got merged into the trunk of Apache after nearly 7 months of debate from all people who participated in it. It was pretty hard for me, but still it went through. Thank you all for anybody who commented on it, made comments, stood up to support us, or gave us advice on how to work through it. So now it has appeared inside Hadoop as HDDS, or Hadoop Distributed Data Store. That name came from the community. Constantine, I don't see him here. He was the one who proposed it. And so that is a name that we have. And what HDDS is it is a module. If you enable it, it loads into your data node so that you can run Ozone in your real cluster, and it'll have no impact if you don't switch it on. If you switch it on, inside the data node, there is a process that gets loaded, and it opens a socket or listens to as a process in the data node so that we can communicate to it and start make things happen. I just want to take one moment and thank everybody who contributed to Ozone. Me and Jayu just stand here and talk about it, but a lot of other people who did the work and make it happen, across the continents, around the globe. Thank you to all. So what is Ozone? Ozone currently is an S3 like an object store. Somebody was asking me yesterday, why is it called Ozone? And the guy who named it was here. I think it is a play on the S3. No, O3, S3, and it became Ozone. So it exposes a REST API and a Hadoop RPC. Just like you would make an HDFS call, it exposes an RPC endpoint. And it also supports a Hadoop compatible file system called Ozone FS. The idea being that if you create a new file system, nobody is going to use it unless you can run applications on top of it. So with Ozone FS, we are able to run Hive, Spark, Yarn, MapReduce. You don't have to make any modification, deploy it, and it just works. Okay, so now I'm going to go into and explain to you what are the abstractions supported within this framework called Ozone, and then we'll show you how it all comes together. So Hadoop distributed data store is basically nothing but a block layer. Remember, that was a promise that long time ago in one of the JIRAs where we discussed. HDFS is this big single monolithic piece which does namespace management. That is, it manages the file names, directories, all those things. And it manages the block information, like where is the block sitting, which data node, oh, is this data node up, is it dead? All those things are managed by that. So what we decided was that if you have, let's say, a 40 gig FS image, it has both the block data and the name data. So somebody has told me that they have such size of images. So let's think of that. Then you can actually, it's a smart idea to just cut into two. Make the block in one file and make the namespace in another space so that we can all scale easily and independently. That is what basically Ozone is all about. So HDDS is a distributed, highly available block storage framework. Now I said all the key magic words, so let's go on. Okay, this is how it really looks like. Okay, so we have something called the storage container manager. I know you don't like the word container. Don't even tell me that. I've heard it too many times. Okay, it is a misuse of that word, so that's why it's a storage container. It's not two words. Storage container is one word. That's what I tell people. Okay, so it's not a container as an independent word. So we have storage container manager, which manages containers. And my friend will explain to you what a container is in a little while. And storage container manager is our block manager, like name node, and it talks to data nodes. And there is this little guy called Apache Ratis sitting down below, and his job is to take a block and make sure it is copied to 3 other nodes. See, that is a promise of HDFS at all points. We could write something and it would have 3 copies. So that guy down below will do that for us, and we'll talk about it in a little while. So what does HDDS give you? So HDDS brings in these functionalities. There is cluster management. Like you want to bring in a data node, you want to decommission a data node, you want to do all kind of operations at the cluster level. Today, name node is capable of doing it. Today, name node is the only guy who does that. And we are saying, no, it should be done by somebody else. Identity, something which is very close to my heart. Years ago, somebody somewhere said it's a smart idea to use certificates with wildcards on a Hadoop cluster, and this myth continues. Okay, so you would see real deployments, real clusters with wildcard certificates in Hadoop world. There might even be documentation in various vendor websites which says, hey, it's a good idea. I can promise you it's there in Apache. Okay, it's actually a bad idea. If you're a security person, somebody tells you go use a certificate with wildcards, you should immediately punch him on the nose. Okay, not me. See, I've never said that, but Hadoop community tends to do this. So one of the things that we have built is an identity management service. In other words, we have a built-in certificate CA infrastructure within that. Then we have block services. That's the whole point. This is a block service, right? It's a block manager. We do replication for you and all the security that comes from based on these identities. So now when a data node boots up, it gets a data node certificate. So if you're a process, you should be able to say, I am a process running on this node, or eventually you will get there once you start using this. And it is, you don't have to touch it. It's hands-free. We will manage everything. We don't expect you to know anything about certificates. For you, as a user, it is invisible. Okay? It is just that you don't have to deploy certificates anymore, especially these wildcard ones. So I'm going to tell you how we will boot up a cluster. At this point, if you have any questions, I can take that, or you can wait till the end, whatever works. Okay? Yeah, go ahead. Eventually, our hope is that we will put it into Hadoop common and will become everybody's common thing. In our first release, that is going to happen in next few months. We would keep it very close and personal. We are not yet reached the sharing mode yet, but hopefully we'll get there. Because once you have it as part of Hadoop, it just makes sense for everybody to use it. So in this, I'm going to tell you how HDDS boots up and what a cluster is. It's slightly different from your current HDFS cluster. So, okay, sorry, let me just go back and tell you. So HDDS is a certificate infrastructure, and what happens is that when SCM boots up, so let me show you this. So this is an SCM. An SCM is just a service that you first start. Think of it like name node, right? You started it up. And what does it do? It basically generates a cluster ID and an SCM ID. A cluster ID is a string which identifies every member inside the system. So data nodes will get it, the name services will get it, the SCM will have it. Now you can create many, many SCMs inside the system. So that's why you have to have an SCM ID also. Then it will generate a self-signed certificate. I'm going to preempt a question. Yes, you can bring your own certificate. Yes, we can be a sub-CA. All that questions are answered. But generally, if you don't have it, boom, you come up, we'll generate a self-signed certificate. Remember I told you, you don't have to know anything about it. So we'll generate the self-signed certificates, and we will wait for data nodes to register. Okay? Now, when data nodes register, they will come in and say, OK, I want to register. They are booting up. They're communicating to SCM. And what they do is that they will create something known as a certificate signing request, or a CSR. So it'll say, I am so-and-so data node. Please give me a certificate. And it'll go to SCM and say, please do that. When that happens, the SCM can auto-approve it if you have Kerberos set up on all your data nodes. But if you're doing a new cluster, we are not going to ask you to set up Kerberos on 3,000 nodes. We think it is much easier for an administrator to just look at the pane and say, yes, this request looks valid. Yes, this request looks valid. Approve it by yourself. And then those certificates will be issued. SCM issues after verifying the identity. So that verifying can be in whatever way you like it. And then the data nodes are functional at this point. So you have a complete working data node. Remember, this is the green picture that I showed you, SCM and the data nodes. What is missing is that we still have no name node. I have a block service. I have data nodes which can take blocks. But how do you create a file? How do you create a key or a volume? And that is done when you add these orange layers. So you can bring in a different name service. So Ozone Manager is our name service. If Jacob Homan is here, I have to just thank him for the name. It used to be called KSM in earlier documents. And he mentioned to me that it is a name in some of a person who was in the FBI wanted list. So they changed it into Ozone Manager. These days we call it OM, just to improve our spiritual experience. So and that is name node prime, because eventually we'll write a new name node which can do this. So I just want to make sure that you understand this, that this is the journey that we are taking to address the name node issue. We have not addressed it yet. Today we are going to talk about this green layer because this is perfectly functional, and that orange box, we don't have that yet. We have not started working on it. Okay? So what an administrator would do is, once this is all booted up, he can now say, add a namespace manager. So you add Ozone Manager, this cluster becomes Ozone. If you add a named node, it becomes HDFS cluster. So we have basically separated a block device, block service into an independent service, which can be consumed by other services like Ozone or HDFS. So now I'll hand over to Jayu to explain how you can use this block thing to read and write data. Thank you.
So now you have a cluster boot up. And what's next? For most developer or user of the cluster, the most important thing, you will be able to dump some data into the cluster. And now I'm going to talk about how you can write data into the cluster. So to write data into the cluster, you need to understand where the data is stored. The data is stored in data node, but not as a single block like HDFS approach. What we are doing is we have an abstraction layer called storage containers. Those storage containers running on each of the individual nodes, and it's provide the basic units of replications. And the size of the container can be ranged from like 2 gig to 16, and it's a configurable value. So the default one we set at 5 GB. That's a pretty decent size for replication engine to work nicely with Ozone. And with this container approach, what we achieve here is we fully distribute the block layer metadata rather than maintaining that like HDFS. in the name node. So the namespace now have a clean metadata, and while the block layer have its metadata, which save like where these blocks are saved and where are those chunk informations. It's fully distributed, so we don't have the burden of maintaining this centralized block map on the name node side. So for the metadata, we use key-value store based on the log structure merge tree-based key-value store. And we have pluggable implementations. Currently, we use RocksDB to save the locations of each of the blocks. And each of the blocks has a list of chunk files, and the chunk files can be like 16 megabytes. So we can have different chunks located across the board on all the volumes of the disk based on the policies where you want the chunks of the blocks to be located. And each chunk file, it has the location and its offset for the block and also the length of the chunk file. And those containers, as I mentioned earlier, is the basic unit of the replication. So you can have multiple containers being replicated across all the data nodes. That guarantee your writes will be always consistent. And with container, we have a notion of open container and a closed container. Open container means the keys and the blocks are in a writable state, which you can always let the writer to write into it. Well, when the container reach certain size or the container have some issues, like some of the data node failures, what we're going to do is to close this container because it's not in a good situation for you to continue write into this container. And that's a very clear notion of between these two states, so that the replication engine will only work with the open container. With the closed container, when the container is closed, and you don't need the Redis, Apache Redis to guarantee the consistency. It's just like a sealed state, and you don't need to worry about the consistency. And when we use container to do the replication, as I mentioned earlier in the previous slides, we use the Apache Redis-based approach. And to do the replication, and usually you need to set up some sort of a pipeline. What is a pipeline? A pipeline is basically a replicated stream, and you can keep writing the data, and the data is guaranteed to be consistent across all the replicas. And like HDFS, when you write a block, you first need to recruit 3 data nodes, and those data nodes set up a pipeline, then you can write to that stream continuously, like to the first data node, and second data node, and third data node, and you get the confirmation that the block is committed, and then you are done with the write. And with HDDS, and we also support different kind of replication strategies. For example, you can choose different pipeline type, and what we default to use Apache Redis-based pipeline. And you can also specify like replication factors and the storage type and all those criteria based on the storage policies. And HDDS use Apache-based replication pipeline. And the reason we choose Redis because it's a highly customizable Java library. And my colleague Mukul has given an excellent talk yesterday about how we achieve high throughput for data replication using Apache Redis. And if this is a Redis pipeline, what we do is you need to find a leader node. And the write will always go to the leader node first and append to the Redis log, and then update the Redis, the wrapped state machine, and then apply to the follower nodes. And this way, once we get a confirmation from the Redis pipeline, then the block is committed, and we're done with the write pass. So to summarize, what we do when the client start writing a key, just like when HDFS client write a file, we first talk to, the client will need to talk to the Ozone manager. And there are multiple protocols, like Anu mentioned earlier. You can use REST, you can use Hadoop RPC, and also there are other, you can use the Hadoop container file system, which is a wrapper of all these transport protocols, to talk to Ozone manager to get a block. And Ozone manager received the request. Ozone manager is just a namespace server. It doesn't manage the block itself. The block layer is handled by the storage container manager. So the corresponding call reach a separate service, which is called the storage container service. The service allocates a block and gives the information to the Ozone manager, and Ozone manager get it back to the client. And to get a block, you have to put the block into some containers. So the container will be associated with the pipeline to do the replications. And in the ideal case, we have some, like, for example, pre-allocated, like, open container with some pipeline already associated with it. So you don't need to set up container pipeline association. And so if it's like a closed up, so you have, or you have some, like, containers has all been closed because they have been used up, then you need to find a new container. And to find a new container, you need to find a pipeline for that container so that container data can be replicated consistently across all the container replicas. And the SCM take care of all the container allocation and the binding of the container into the pipelines. Once this pipeline and container setup is done, we have a fully functional open container for the client to be able to read and write data into that containers. And the SCM, during the whole process, SCM persists. The only information that SCM persists is the container information. So the container ID, along with the container, like the size and all the storage related informations into a similar RocksDB key value store. And the good thing about this is we don't have maintain everything in memory, so it's based on your workload. Only the active working set will be loaded into the memory, and all the others will be just in the disk. And we will leverage all the benefits of the faster SSD storage for quick metadata access without GC pressures like HDFS namenode has. So once the client gets allocated a block, and what the client gets is basically a block ID. What is a block ID? A block ID is basically a container ID plus the local ID, which is allocated automatically increment within the containers. And along with the block ID, the Ozone manager also gives is the pipeline information. The pipeline, as mentioned earlier, is basically a replicated stream with 3 replicas, like the data node informations. And the client uses the container, the block ID, along with the pipeline, and to access, to read and write the data. And so to summarize, we have just to go over the first 2 process of how you write the data. This is the commit protocols for the Ozone client. Ozone client put key, and the Ozone manager requests the block, get the block ID and the pipeline information to the client. What the client does is basically find the pipeline and get connect to the leader node and write data as chunks and update what the data node side, the container metadata, get the block and the chunk information updated into its metadata, as shown in the right side. The block and its list of chunks on the data node get updated, and this all like local decisions, and without any needed to update like the SCM. SCM is just purely maintaining the container information and no blocks information at all. And when the client finishes write the data, it's basically the last phase of the commit protocol is to commit the key so that Ozone manager get the final length of the key available for the client to read from. And the Ozone manager has its metadata. It's also a very simple metadata structure compared with the way HDFS maintained it. It's basically a key name as the key values, the key of the key value store, plus the list of blocks, and also some of the commit key length, which is the available length for the readers. And so the key has the third phase for commit. So before it's commit, it's basically when you want to write data, the key is in an open state. And open state, which means the commit length is subject to change, and you can only read from the last commit length. And once client finish the third phase of commit, the commit length get updated, and the key get closed state. So the closed state is where you can reliably read, but the open key, you can only read to the last commit state. And if some client fail to commit the key, and the key will get garbage collected because it's expired. And compared with HDFS, the reading process is pretty similar. And the client needs to talk to the owner manager, get the list of the block information, and talk to the data node to retrieve the blocks. And there are some, the basic operation for the client is like a read, write, and the third one is the delete. To handle delete, and we have two types of containers, open containers and closed containers. Let's talk about the closed container because it's in a state that's immutable. And supposedly, like, there is no writer for it. And so the deletion can be easily handled because when the client, the algorithm is like very simple. When the client deletes a key, the list of blocks will be added to the SCM delete log. And the delete log will be sorted by the data node and the containers and sent to the data node where the heartbeat. So when the data node finish all the deletions, and the corresponding transaction ID was sent back along with the heartbeat, and once the confirmation is received from SCM just clear the delete log, and if there are some data node doesn't finish it, and then the SCM will keep retry until the key is deleted. And for the open container, we actually have some choices. We can basically use the Apache Redis to do the delete based on the Redis pipeline, but we choose to do it in a way similar to closed container for some consistency, also some of the performance, because the deletion can be heavy operations on the data node side. So if we hold off the actual operations on the deletion, and some of the write and the read operation maybe get impacted. So we hold the delete log for the open containers and wait until the container get closed. And at that time, we will send the deletion log to the data node, just like we handle the closed container, because that time the container is closed, it's in a state similar to the closed container. So it's a uniform process for deletion processing. And at this time, I will hand it over to Anu to talk about the scaling part of HDDS.
Hi. Okay, thank you, Shayu. So the key takeaway is that Ozone, you can now read, write, and delete stuff. It works. Okay, so please, that is the whole aim of us explaining this very complicated protocol to you. For you, it just works. Okay, that's what our job is, basically to make it work. So I want to show you how we will scale Ozone. Okay, so thank you. So I have 5 minutes, so I'm going to go slightly fast. This is a typical deployment of SCM. You see an Ozone manager, there is an SCM and a bunch of data nodes which gets managed. This is how HDFS looks like. I mean, in this picture, all you see is that you have a namespace. We separated it out of the block space. They're separate and they're standing around. But remember that we said when you create a cluster, you create a block service, and then you create name services. Nothing prevents you from creating 3, 5, 10, 200 Ozone managers running against an SCM. So you can scale the name part completely independent of the block layer. For example, let us say that you're a company where you have a web service sitting in the right in the front, which writes 5-byte files into Kafka, and Kafka ends up writing that to HDFS. Yes, now you can do that, because now you can set up, because that part is just very largely overloaded for name, because they are not using any space. So you want to scale the names part. Okay, but you could be a self-driving company, car driving company, which runs and takes photographs or videos, writes this 50 GB files into the cluster. Okay, there is no name load, but your blocks are heavily loaded, because every file you put, maybe you have only 200,000 files, but you have 50 gig files, each one of them. In that case, you really want to have a lot of data nodes, and you want large number of block services. See, we separated them. So you go and scale the SCM part up. We don't really care. Now, see, if you can scale all of that independently, you can do this too. It's just a programmer's fancy because it gives me closure, right? If you can do that, you can do this. There is no real reason to do this, but hey, you can, so you do it, right? So that is how we intend to scale Ozone. Now I have a bunch of slides on ozone security. I'm going to go very rapidly because she has already given me a warning. The security is based on Kerberos, just like the classical architecture. SCM and Ohm will speak Kerberos just like you are familiar with. And they will return you a delegation token and a block token. That's why Spark works. That is why Yarn works. They all think it is exactly the same thing. Okay? And once you have that, so there is a small dance here. The data nodes know only about the SCM. So who's this Ohm who's telling me to allow somebody to read a block? Or the name node to allow you to read a block? That's why we have a certificate infrastructure in place, because every token that we issue, it is signed by, let's say, Ohm. But Ohm says, hey, I am signing this, but do you know who I am? SCM says you should trust me. And data nodes only trust SCM. So SCM says this is Ohm, and Ohm says please give this access to this block. And because of that, data nodes will say yes, you can now read it. But from an application's perspective, it is just a block token. They take it, they go it, they give it to the data node. Data node says yes, you got your data, go work with it. So there are a lot of details. This is for the slides. If you're looking at it later, you can see the information. But we have done tremendous amount of work on this, and it is at a state where it's pretty close to being functional. Okay, and we are now working on, we have 3 branches still in progress. So even this is why we don't yet have a release. We are working on this where we have an branch 151, where we are starting to work on the HA aspects of SCM and Ohm. We want it to be highly available. We have pluggable container storage IO layer. This is again a very geeky thing. Bring your own containers. Somebody might say, hey, you know what? I don't like Ozone containers, or I want you to do something else with it. I want to use this block layer, but I want to control how the data is laid out. And also, there is another important reason that when you migrate from HDFS to Ozone, people want something called an in-place upgrade. I tried to convince them that it's not a good idea, and people said, nope, we are not transferring 4 TB or 4 PB of our data via copy. No CP is ever going to work, so you better get this done. So that allows us to define new formats of containers. Like we can say, oh, this HDFS blocks is now in this container. Without any copy, we can just fake that. We just have to create the metadata. So that work is being done in that branch. It should get merged very soon. We'll send out a request to the community pretty soon. And the security work is in a branch called HDDS 4. So these things, we are trying to get it together for our first release. And we are out of time. If you have any questions, we are going to host a web page. I'm going to be in Ask Me Anything counter. I'll show you a demo. Come there, this works. Okay? So please do come talk to me. I'm going to stand there all day. And if you have any questions, I'll take them now. Go ahead.
Service use the Ozone layer. It's not something that's kind of a silver bullet that can divert certain operations to use Ozone instead of using HDFS for like app logs.
Oh, you can certainly do that. Let me just repeat his question. What he's saying is that, look, if I deploy Ozone, can I just get some services to use Ozone and rest of it to use HDFS? The answer is yes, because HDFS traditionally supports a protocol. Like you can say S3:::. Just like that, you can say, if your app logs, when they write, you just have to say, use this URL O3:::. Yeah, instead of HDFS:::, put O3 there, it'll go into Ozone completely. So yes, that is one of the major, yeah, go ahead.
How does it compare to HDFS in terms of performance?
A good question. My boss is going to shoot me when I answer that, but I'm going to take the risk. I'm just going to gamble that he does not have the gun with him today. So our aim is to be as good as HDFS when we release. I can tell you that our performance numbers ranges between 80 Mbps doing one stream, one thread at this point to 140 MB per second. This is a similar hardware. When we run HDFS on the hardware, we get very close performance, but we have not tuned our system yet. So that's why I'm not supposed to answer it, because we just want to come out with a bang rather than how we evolved. We just want to look cool when the day we were born. So, But this is the numbers that we have. We run performance numbers every day. So this is what we have today. Yeah, go ahead. Does it support update upserts? No, it does not. When you do a put, it overwrites the file right now. But we will eventually support append and overwrites to a file. But that's another talk. Next year I'll come here and talk about that. Any other questions?
Do you have any commitments from Hortonworks or Cloudera about being bundled and supported in a distribution?
Yes, but I don't think I should be able to answer it today because it's a Hortonworks question. I'm here as a developer Apache, so I'm going to take a rain check on that thing and we'll answer it to you later. Okay?
The overall goal is to eventually, if possible, to have it in the ecosystem of like
Oh, this is checked in as part of Hadoop. You get the code out, Hadoop code out, you will see all of this, everything working. And we have instructions, so you're most welcome. If you come over to the Ask Me Anything counter, I can show you the code, build it, and we can run it together. You're most welcome to do that.